now we will have our final lecture on robust auction design. So let me just first recap the question that we are trying to address in these lectures. Okay, so imagine you are a seller of a good. You know the set of bidders, right? You know the distribution of bidders' value, but you are uncertain about the model of bidders' information, and you cannot quantify this uncertainty in terms of a Bayesian prior. Okay, so the question that we are trying to address is, what auction should you run? Okay, so here is an answer. This is not the answer, but we claim that in many cases, the auction that you should run is what we call a proportional auction. Okay, so in a proportional auction, the action space or the bid space is just any positive number, the space of positive numbers. That's what you can bid in the auction. And then your allocation is a ratio between your bid and the aggregate bid. Okay, so by aggregate bid, I just mean just add up everyone's bid. So this sigma notation is just means is just a shorthand for summation. Okay, so you get a proportional allocation of a simple total supply function, which is a function of the aggregate bid again, and it takes a very simple form. So it just depends on a threshold x star. If the aggregate bid is bigger than the threshold, then everything is up for auction. Okay, so the total supply is 1 when the aggregate bid is bigger than or equal to x star. And if the aggregate bid is less than x star, the threshold, then the total amount of the good up for auction is just depends on the ratio between the aggregate bid and the threshold. Okay, so this should be x star. Okay, so that's a very simple, intuitive form for the allocation. And then for the transfer function, it's again proportional. So you pay a proportion of a total transfer function, which depends on, again, the sum of the bid. So the total transfer only depends on the aggregate bid. And then your individual transfer is a proportional fraction of this total transfer function. Okay, so this means that right in this auction that we propose, the unit price, the price per unit that you pay is the same for everyone. So we have uniform pricing, and also this uniform, the same price per unit is a function only of the aggregate bid, only of the summation of the bid that everyone submit. Okay, so we will claim this is the right auction in many settings. So to be more precise, so let me go quickly go through the model. Okay, so here we have, as we have assumed in these lectures, we have a single unit for sale. We have n bidders whose value is just a number because there's only a single good up for auction. Okay, and then so we said that as sellers, we know we can quantify the prior distribution mu over the value. So we know this mu, which is a distribution over joint distribution over everyone's value. And then as sellers, we are allowed to use any mechanism. Okay, so again, mechanism just has a action space for every bidder. And then we have an allocation function which maps from the space of action to an allocation. The allocation may be divisible, it may be stochastic. And then we have the transfer function, which maps from action profile to how much money that each bidder should pay. We assume there is a way to opt out of the auction, opt out of the mechanism. So we assume there exists an action, let's call that 0. When you submit 0, you pay nothing. You may still get some positive allocation, but that's fine from your perspective because your value is weakly positive. So you are more than happy to get some free allocation as long as you don't pay anything when you bid 0. Okay, so we call this this class of these mechanism participation secure mechanism. Okay, so we let M denote the set of participation secure mechanisms. Okay, so basically mechanism is defines a simultaneous move game. Of course, we have to also specify information structure or the type space to complete the specification of the Bayesian game. Okay, so information structure has a signal space for every bidder. Each bidder observes the realization of his or her signal. And then the information structure just has a joint distribution over the set of signals and the set of values, with the caveat that the marginal distribution on the value is mu, which is what the setter knows. Okay, so we let this bold I to denote the set of information structures. And then finally, given the Bayesian game defined by a mechanism and an information structure, we use the standard Bayes-Nash equilibrium solution concept to make prediction. And then we assume that the seller wants to maximize profit or revenue, which is just expected total transfer in equilibrium, given the distribution of signal specified by the information structure, sigma. Okay, so in this setup, so a general result that we are able to prove is a minimax theorem. Okay, so here, okay, under some technical assumption that every value profile has positive probability. Suppose we look at a finite setting at first. Okay, so suppose a value is finite, actions are finite, and also signals are finite. Then in this setting, as a seller, one thing which is natural is you want to maximize over the set of finite mechanisms, but you imagine there is an adversarial nature who is choosing the worst case information structure given your mechanism that you choose initially. And also, right, imagine that the adversarial nature is also choosing the worst case equilibrium. Okay, so this is the relevant revenue benchmark. This you take soup over mechanism, but inf over information as well as equilibrium. So we call this left-hand side max to mean to emphasize that this is right. There's two minimization going on here, minimization over information as well as equilibrium. But on the right-hand side, we are saying that suppose the adversarial nature is moving first, choosing some information structure, and then we are able to see that information structure, and then we can choose a mechanism to best respond to the information structure, and also we just we are able to choose the best case equilibrium from our perspective as seller. Okay, so that's the equilibrium revenue. So, right, our minimax theorem says that these two problems have the same value. Okay, so this is, we call this the strong minimax theorem because of the because here who gets to select the equilibrium is different across the two sides. Okay, so here this profit guarantee, right, given from these programs, they are robust to the selection of equilibrium. Who gets to select the equilibrium doesn't matter. Okay, because if we fix any equilibrium selection rule, we will just get something in between these two sides, right? Because given any selection of equilibrium, we get something here, but if the two sides are the same, then they must be the same, whatever the equilibrium selection rule that we use. Okay, so one interesting implication of this strong minimax theorem is that for the exercise of designing max-min mechanism, equilibrium selection does not matter. Let me emphasize that we are building on the work of Chang and Ely, right? This gives us a saddle point, right? If this mechanism solves the problem on the left-hand side, and if the information structure solves this information design problem on the right-hand side, then we will have a saddle point in which the mechanism is optimal on this information structure. At the same time, the information structure here is a worst-case information structure on the mechanism, which is exactly the saddle point constructed by Chang and Ely as well. Okay, so the difference here, of course, is that, right, recall Chang and Ely's result as presented by Ben in lecture 2. Here we have we do not necessarily have private value. The information structure are restricted to be common prior information structure. And we have robustness with respect to the equilibrium selection. We do not necessarily select the seller preferred equilibrium. But nevertheless, we have a very similar flavor of result. Okay, so let me go through and let me show you. Actually, let me show you a stronger theorem, which give insights to the solution of these max-min problems, and also in some cases give us an exact characterization of the solution. Okay, so to solve these max-min and min-max problems, we will look at a sequence of linear program which relax the problem. Okay, so we will look at linear program which give us lower bounds and upper bounds on max to min and min to max. Okay, so first of all, let us give some labels to the action space and also to the signal space. So let's put just a one-dimensional order on the action and signal space. Let us call the action space and signal space xi, x. So here I just have a grid where the size of the grid is 1/k, and then, right, the minimum action or signal is 0, the maximum action and signal is k. Okay, and then I'm going to take k to infinity, so the upper bound on x goes to infinity. Simultaneously, the size of the grid goes to 0, so we have an approximation of the positive real line as k goes to infinity. Okay, so here, right, so if we restrict action space to x as defined here, then, right, we can restate our max to min problem as here, right, all I'm doing is just saying that you have to choose actions from this set, but doesn't really make any difference, right? The only difference this imposes here in this MK, where the actions are XK, is that we just have 2K plus 1, well, actually K square number of actions for each bidders. But the label of these actions so far has no meaning, right? Because the meaning of the actions is determined by the equilibrium. Okay, so here, suppose we are just looking at restricting to a mechanism where the actions, right, only the cardinality of these actions matters. And likewise, we can look at the information design problem, mean to max, where nature is restricted to signals defined here with these labels. Okay, so here, right, so far we have not relaxed the problem at all. But, okay, so let me, before going to the relaxed problem, let me just define some notation which is crucial to our construction. So basically, we will be looking at discrete derivative. Okay, so the grid size is 1 over k. Okay, so this is, so del I is a discrete derivative. And this plus means that we are looking upward. We are looking local upwards. Okay, so that's that. So here is where these orders on the xi becomes important, because the orders will enable us to define discrete upward derivative. Okay, and this is right. This is not a typo. Actually, it becomes convenient to normalize the discrete derivative not by k but by k minus 1. Okay, but of course, when k is large, this is almost basically the same as the usual definition of discrete derivative. Okay, so and then given discrete derivative, we can define the discrete gradient vector, which is just the profile of these partial discrete derivatives. And then here, this is right del dot f. That is the so-called discrete divergence. Okay, in the discrete divergence, we are just adding up these discrete derivatives. Okay, so with these notations, now we can define, first of all, the linear relaxation to the Seller's problem, to the max to min problem. Okay, so we are maximizing over allocation and transfer, and this lambda, I will explain now what is lambda. Okay, but so here, so first of all, I will explain in the next slide the meaning of this linear relaxation. But first of all, let me just note that this is a linear programming problem. Okay, so this is a tractable linear relaxation program. I will claim that in our original problem, it is actually a nonlinear problem. And that is also one reason to relax those problems. Okay, so this program is really tractable because it's linear. Okay, so essentially, this is maximizing over mechanism a lower bound on the revenue across these mechanisms subject to some local IC condition. Okay, so let me explain. Okay, so suppose—
Songzi, could you say a little bit about what makes the original problem nonlinear?
Oh, okay, so actually that is best explained here in this slide. Okay, so first of all, let us just fix one mechanism. So fix Q and T. Okay, so remember, Ben talked about base correlated equilibrium. Okay, so that's just a combination of information as well as equilibrium. Okay, so one natural lower bound on the for a fixed mechanism for the equilibrium revenue is we just minimize across base correlated equilibrium for the fixed mechanism. Okay, so that is written on the left-hand side. Except I'm just looking at a local BCE, right? I'm just looking at local obedience constraint. Okay, so recall that in base correlated equilibrium, right? Base correlated equilibrium is a distribution over the action and the state. The state here are the volume profile, right? Action is X. Okay, so BCE is a sigma distribution where the marginal is has exactly the right marginal. It agrees with mu, the prior distribution of the seller. And then this is an incentive constraint, except I'm just looking at local incentive constraint. Okay, so this constraint just says that when you are recommended to play Xi in this fixed mechanism, you do not have any incentive to deviate to Xi plus 1 over K, right? The next actions in the grid. Okay, so these incentive defined by the discrete derivative, right, on average has expectation less than or equal to 0, conditioning on your recommendation Xi. Okay, so the reason that we look at local BCE is related to what Ben talked about in the large part of the previous lecture, right? There we have seen that just focusing on local incentive, right? Just with a very simple mechanism, we can already have very powerful revenue guarantee. Okay, so that motivates us to just focus on local incentive. Okay, so here, right, so that's why we just minimize for this kind of lower bound on the equilibrium revenue across information. We look at local BCE. So, right, so this lower bound is going to be even lower than what we will get by minimizing across all BCE. By adding more constraint, we will only get a higher minimization problem. So this is a valid lower bound on our revenue guarantee. Okay, so a standard construction is just to go to the dual of this problem. Okay, so right, so lambda, right, the dual variable for the marginal constraint, let's call that lambda. And then the dual, the multiplier on the local obedience constraint for each Xi, let's call that alpha. Okay, so that's right. So it's straightforward to work out the dual of this minimization across local BCE problem takes this form. And then what we want to do is, right, so we have this revenue guarantee for a fixed mechanism. Then clearly what we want to do is to maximize this guarantee across all feasible mechanisms. Okay, and so this is why, so here notice that we have a interaction between alpha, the multiplier on the local incentive constraint, and the mechanism variables, which is Q and T. Okay, so if we do this problem here, maximizing this lower bound across mechanism, this is still not a tractable problem because this is not a linear programming problem. We have alpha multiplying the discrete derivative of the transfer as well as the allocation. Okay, so that's why our original problem is nonlinear. Okay, so what we want to do is just to say, let's fix a particular value for these local obedience constraint. We let us just take their multiplier. Let's just say exogenously their multiplier is exactly 1. Okay, so that's right. If we do that, this is a maximization problem, right? If we just put some value for alpha, we are going to get a lower value for this maximization, but that's fine because here we are looking for a lower bound on max to mean. Okay, so this is legitimate. Okay, and in some sense, this is without loss because, right, because we have control over the discrete derivative of Q and T. So we can sort of compensate value, right? When we impose this, then we can compensate alpha for any particular value for alpha by just changing the discrete difference between Q at consecutive action profile. Okay, so in some sense, that is without loss. Okay, so by putting, by letting multiplier for the local obedience constraint to be 1, we get exactly this linear program. Okay, so that's our first linear relaxation for max to mean for the Sellers problem. Okay, so for the nature's problem, okay, so let's use a censored geometric distribution on our grid xi. Okay, so this is just a geometric distribution with arrival rate equal to 1 over k. And also we have, it is a censored geometric distribution. So we put all of the probability math on this. We have an atom on xi equal to k. Okay, essentially a geometric distribution is on all positive integer. But for integers outside of our grid, we put all of those mass outside of our grid on the highest signals in our grid. So that's why we have this, right? We do not, right? We have this factor 1 over k for every signal realization except the highest realization, because, right? Because we have that mass which exactly cancel out this factor 1 over k. Okay, so let us suppose the signal are independent across the bidders. Okay, so we have censored geometric distribution for every individual bidders, and then we just multiply them together to get the probability mass function for a signal profile x. Okay, so our linear relaxation for nature's problem, this mean to max problem, well, looks very familiar. So here we are minimizing across information structure sigma, right? This joint distribution between signals and values. Okay, subject to the constraint that they have the right marginal, right? The marginal on the value is given by mu. The marginal on the signal is given by the previous censored geometric distribution. Okay, so and then what we want to do is we define the interim expected value function as a function of the signal profile. The last constraint, what we are doing is just the standard construction of, for a fixed signal profile, we maximize the virtual value across the bidder. Okay, so this is a virtual value. Okay, so here we are using the formula from Bülow and Klemper's model in the first lecture. Okay, so one nice thing about the hazard rate, about the censored geometric distribution, is that the inverse hazard rate, right? Inverse hazard rate should be this, right? The probability density, which is basically k times that. And in the numerator, we should have the probability that we have, right, the probability of having a higher signal than xi. Okay, so sum over xi prime bigger than xi. Okay, so you can show that this is exactly 1, which is also the reason that we work with censored geometric distribution, right? So this derivative, right, is really multiplied by 1 here. So that's exactly the formula for virtual value from Bülow and Klemper from their interdependent value model, where everyone has independent and geometrically distributed signals. Okay. Okay, so this is right. It doesn't really matter here that right here, it may be the case that this virtual value is decreasing with the signal realization, but that is fine because we are just getting an upper bound, right? We are getting a linear relaxation for nature here. So this is an upper bound. So it doesn't matter, even if the virtual value decreases with signal, we still have a valid upper bound on the equilibrium revenue. Okay, so this is also legitimate. Okay, so this gamma variable is just picking out the maximum virtual value across the bidder. Okay, and then we multiply by the probability of that signal. So we are just getting the, here we are getting on average the maximum virtual value across all these signal profile, with a caveat that, right, gamma has to be positive, right? That's built into the program. So if the virtual value is negative, we don't take it, right? Because the seller has the option of withholding the good. Okay, so here already you can see there is some relationship between this program and the previous program. Okay, so because remember, right, in the first lecture, I talked about if we take the dual perspective on Bülow and Klemper, right, we can have, right, essentially in the dual formulation, the optimal multiplier on the local IC constraint is exactly the inverse hazard rate. Okay, so the inverse hazard rate is 1. Right, which happens to be also the multiplier that we have chosen in our other program, in the previous program right here. Okay, so already, right, although these is not apparent that there are any relationship between these two programs, but we are choosing the same value for the local incentive constraint. And also, we are also just using local incentive constraint in both programs, because as you recall from lecture 1, to derive virtual value, essentially we are taking local constraint as binding and we are solving out transfers. Okay, so we are doing very similar things across these two programs. And in fact, I will show you next that these two programs, they are basically the same program as k goes to infinity. Okay, so that is the claim. Okay, so as k goes to infinity, so first of all, for any fixed k, they are relaxation. Okay, so the right, so for min to max, we get a upper bound. For max to min in the first program, we get a lower bound. So that is valid for any finite k. But as k goes to infinity, these two linear relaxation, they will converge to each other. Since our original max to min and min to max are sandwiched between these two bounds, they will also converge to each other. And that implies the original strong minimax theorem that max to min is equal to min to max, because these bounding programs converge. Okay, and also, right, just from our discussion earlier, if we get any mechanism that solve the bounding program for the max to min, we get a mechanism whose revenue guarantee is what it is given, what is their value from that bounding program. And likewise, for the information design problem as well. Same, and we have the similar upper bound for the profit guarantee for the linear relaxation for min to max as well. Okay, so it is without really, right, what we are claiming here is it is without loss to study the bounding program, right, when K is large, and any solution to the bounding program will give us the optimal profit guarantee when K is large. Okay, so let me explain these two bounding programs. Okay, so I have rewritten them here, right? This is problem 1 is the bounding program for max to min. Problem 2 is the bounding program for min to max. Okay, so here this is right. Remember in problem 2, right, to drive at the virtual value, right? The step is to solve out the transfer. Okay, so right, to solve out the transfer, we arrive at the virtual value. Okay, so we can do the similar exercise in 1 for the relaxation for max to min, right? So here, right, we have transfer here. Okay, so we can redefine that to be psi, right, for every x, right? We can try to solve our transfer as we did in lecture 1, right? But except that we do that for the max to min auction design problem here. Okay, so this is not free, right? Even though Ti is unconstrained, but remember at 0, Ti has to be 0, right? Whatever the action taken by the other bidders. Okay, so if we redefine this to be psi, right, there is some constraint which turns out to be just that if psi has expected value equal to 0 according to the censored geometric distribution, then we can always find transfers in which, right, we call this the total, we call psi the aggregate excess growth for the transfer, right, because that is a difference between the derivative and the transfer function, the actual value for the transfer function. Okay, so this is how much the derivative, the growth is bigger than the transfer. The growth in transfer is bigger than the transfer. So we call that the excess growth. And then aggregate just means that we are summing across the bidders. Okay, so the necessary and sufficient condition is that these these aggregate excess growth integrates to 0 if we use censored geometric distribution. Okay, so that just follows, that is implied by Farkas' lemma. Okay, so we can just redefine psi here, and then we would be solving out the transfers, right? So we no longer have transfers, and then we just have psi, which is total excess growth. Remember, this is 0, right? So we can either put in the constraint that this is 0, so that they are valid at total excess growth, or we can just put that in the objective and then let it to be unconstrained. They are equivalent. Okay, so in this, right, we call this 1 prime because that is the version of 1, the linear relaxation for max to min, where we have solved out the transfer. Okay, and that seems like the right thing to do because, of course, in 2, to arrive at virtual value, we implicitly solved out the transfer to get virtual value. Okay, and also this is formally the right thing to do as well, because, right, so let me take dual problem once again. Okay, so let me just call, right, this, right, remember we called the multiplier on the marginal constraint for value lambda. Okay, and let me claim, right, let me call this psi. Okay, so the marginal constraint on the signal, suppose we call the dual variable the multiplier psi. Okay, and for the final constraint, okay, let me call that qi of x, the allocation function. Okay, so if we obviously I'm trying to relate it to problem 1. Suppose we take those dual variables and then just take the dual, we will get back a very almost exactly the same problem as the max to min problem. With the only difference is that right here, right, whenever we take the dual, all of the upward, usually the upward derivative will become downward derivative. That's just the nature of taking the dual problem. Okay, so in fact, right, you can see that here, right, because here on the right-hand side, we have these distribution mu and rho, right? So whenever you take the dual, these right-hand side variables will goes up to the objective. Okay, so you can kind of see that at least the objective is exactly right. And that is also the objective in the relaxed problem for max to min as well. Okay, and then and in fact this is exactly the right dual problem. Okay, so now we have seen that they are almost the same problem. The only difference is that we have local downward incentive constraint for min to max, but we have local upwards incentive constraint for max to min. Okay, so in our final proof, to show that in the final step of the proof, we need to show that this doesn't matter, right? Intuitively, it shouldn't matter when the grid size is small, right? As k goes to infinity, right? Whether you look at upward derivative or downward derivative, it doesn't matter at all. Okay, and that's a final proof, which actually turns out to be quite tricky to exactly show. We have to do a little shifting argument. So basically, to convert this to that, right, we have to move these allocation around. But when we do that, right, when we do the shift, right, when we shift up the allocation so that the downward derivative becomes exactly by construction upward derivative, right, we run into some problem because we have this feasibility constraint which could be violated when we do this shifting to convert local to convert downward derivative into an upward derivative. Okay, so we have to be very careful. We have to do some rescaling and then carefully show that when k is large, it doesn't change the objective by that much, but they can be accomplished. Okay, so really the takeaway is that as k goes to infinity, these two relaxed problems, right, on the left-hand side, we have a relaxed problem for the seller's robust auction design problem solving max to min. On the right-hand side, we have the problem of a nature solving min to max, trying to design the worst case information structure. So really the takeaway is that in the continuum, they are dual of each other. Okay, so we can, and then we can write out the multipliers here. Okay, so this is very helpful when we actually want to analytically solve these two problems. Okay, because suppose they are exactly dual in the continuum limit as k goes to infinity, then we can use complementary slackness condition, which should characterize optimal solutions between these two programs if they are dual problems to each other, right? So this means that, right, for example, if sigma xv is positive, right, then, right, if this multiplier is positive, which means that in the worst case information, we have a positive probability between signal X and value V, then this constraint should be binding. Okay, and this constraint, remember, is quite important because Kasai is the total revenue, and then subtracted the divergence in the transfer. Okay, so this is exactly the kind of condition which can relate local incentive conditions to revenue. Right? We can leverage what we know, assumption about local incentive to get some bound on the revenue, as Ben talked about in the last part of the previous lecture. Okay, so this is, right, suppose we know this is binding, that's very helpful for us to work out the functional form on the mechanism. Okay, so let me go through a quick illustration in the simplest case in which value is binary, and also with probability 1, value is exactly the same. Okay, so this is the binary value, common value case. Okay, so effectively we are assuming that seller only knows the expected common value. Really, value can have any realization which is positive and in between 0 and 1, but they are just constrained to have the expected value which the seller knows exactly, right? Because it's well known that just this known expected value case is exactly equivalent to say that the exposed value is binary and either 0 or 1. Okay, so in this simple case, so here, right, so first of all, as we take k to infinity, the censored geometric distribution will converge to the exponential distribution because, because in the exponential distribution, we also have a hazard rate which is constant and in fact equal to 1. Okay, so that's of course an analog. That's a limit as k goes to infinity. Okay, so we can assume that the distribution in the limit is an exponential distribution with unit arrival rate. And then suppose let's look at this candidate for the interim expected value. Okay, so here, because we specialize to common value, so everyone has exactly the same interim expected value given a profile of signal X. Okay, so let's assume it also have an exponential functional form. So the interim expected value is some constant times the exponential function of the total signal, the aggregate signal, right? The summation across the signal, right? That's the function, the interim expected value only depends on the summation across the signal. Okay, and then this is interim expected value cannot be bigger than 1. Okay, so that's why we need to put a cutoff somewhere, X star. Okay, so when it's less than the cutoff, then it's this exponential function of the aggregate signal. And then when it is bigger than the aggregate signal is bigger than the cutoff, then we just have 1 for the interim expected value. Okay, so of course, right, then this we have a smooth pasting condition here, which actually defines this constant in terms of the cutoff. And then this cutoff is chosen so that we have the right expected value, which is what we start with. This is what a seller knows. Okay, so from the seller's expected value that he knows, it will exactly pins down this X star. Okay, so suppose we work with this interim expected value. So obviously the implied virtual value, right, W minus the partial derivative of w is exactly 0 in this case, right? Because the derivative of an exponential function is the exponential function itself. Okay, on the other hand, the virtual value is equal to 1 in the high region, where the interim value is equal to 1, because of course the derivative is 0 in the high region. Okay, so this is true for every bidders, because every bidders have exactly the same interim expected value. Okay, so in terms of, right, so if we go back to the linear program, what we are saying is that this constraint can always be binding, right? This constraint holds with really with the equality here, right? Because in this constraint we are maximizing, right? We are kind of maximizing the virtual value across bidders, but all of the bidders by construction have the same virtual value. So this constraint can always taken to be a binding constraint. So this constraint is always binding. Then by complementary slackness, this means that this, right, if the constraint is binding, then the multiplier can be anything. Okay, so this means that the seller is free to use any interior allocation function. He can use any randomization in his allocation between the bidders, right, by complementary slackness, because this is a bounding constraint. So the multiplier can be anything. Okay, so this is quite intuitive because, right, because if the virtual value is the same, right, it means intuitively that seller is indifferent between allocating to any bidder. And in fact, this is technically implied by complementary slackness. It has to be, the seller has to be indifferent. His allocation can be anything. Okay, and also, right, remember, right, when gamma x is positive in the high region, right? So here, this is gamma, on the other hand, is a multiplier on this constraint, which means that in this case, then, right, so basically this has to be binding. Okay, so which means that on the high region, seller has to fully allocate all of the good. He cannot have any positive rationing, right? Because gamma is equal to 1. Gamma is the probability rho times virtual value, which is 1 in the high region. Okay, so we know that, right? So this gives us conditions on the max to min mechanism, because it has to be fully allocating when the aggregate bid is above the threshold. Okay. Okay, and then likewise, right, we can do the similar analysis for sigma, right? So remember, according to this this conjecture of the interim expected value, right? It is interior, right? It's in between 0 and 1 in the low region, which means that in terms of sigma, in terms of the actual distribution, between 0 and 1 for the common value, we have, right, interior, right, sigma xv is positive for both 0 and 1 common value in the low region. But this sigma distribution is putting probability 1 on the high region on common value being exactly equal to 1. Okay, so which means that this constraint, which relates the total transfer to the local incentive, have to be binding for both the 0 and 1 common value in the low region, but binding only for the common value equal to 1 in the high region, right? Because again, going back to these two linear programs, by complementary slackness, this distribution from the information structure is actually the multiplier on this constraint, which relates total transfer to total local incentive for all of the bidders. Okay, so that's that's going to be very helpful. So first of all, right, there are a clear condition that these can be satisfied. So with some boundary conditions, then Q has to be linear in the low region, right? So the partial derivative has to be exactly constant, and it turns out to, right, there's additional condition. In fact, the partial derivative for the transfer is exactly 1 over x star, where x star, remember, is a cutoff on the aggregate bit, or the aggregate signal as well. And then in the high region, we must have a upper bound on the derivative of the allocation. Okay, so it has to be less than 1 over x star. Okay, so that's those are necessary, and in fact, they are also sufficient for max to mean. But one very interesting and important allocation which satisfies these necessary and sufficient condition is the proportional allocation that I talked about in the beginning of the lecture. Okay, so on the other hand, there are other, right, clearly there are other mechanism allocation which satisfy these conditions as well, because, right, but just for the proportional allocation, you can see that, right, when in the low region, when the aggregate bit is below the threshold x star, then this is, of course, this is a linear function. Allocation is a linear function, right, when sigma x is below x star, with exactly the right derivative as required in these conditions. Okay, and finally, right, so we said that these constraint has to be always binding in when v is equal to 1. Okay, so so if we know what is the allocation, we can work out the transfer, right? Because by definition, transfer has to have these total excess growth. Okay, so we have a first order partial differential equation to solve for the transfer. And then, right, what is nice about proportional allocation is that it will have a very simple solution to these partial differential equation, right? Turns out that the transfer is also proportional. This also solves this partial differential equation, right? Turns out that what is nice is that the total transfer, that the total revenue that the bidder pays is a function only of the total bids that everyone submit in the auction. So this is right because by having the proportional functional form, this partial differential equation will reduce to a nice and simple ordinary differential equation. Okay, so that's this simplicity of the allocation and transfer functions makes the proportional auction quite special. Okay, and then and finally, in these linear programs, we have used revelation principles, right? We have used direct mechanism, and we used base correlated equilibrium. Okay, so we have used 2 revelation principles in these bounding programs. And so if they converge to each other intuitively, we should expect the solution, the saddle point mechanism and information structure is such that truth telling and obedience is at least locally optimal. And in fact, we can directly verify not only they are local, it is a local equilibrium, it is a full equilibrium where there is no incentive to deviate anywhere, local or global. Okay, so this can be directly verified. So okay, so this is just right. I just talked about a simple binary common value case. So we can generalize it in two directions. Okay, so suppose we make the value common, but not necessarily binary, right? We can show that proportional auctions remains max to min optimal. Okay, so proportional auction works even beyond the simple and stylized binary common value setting. For any common value distribution, proportional auction is max to min. Okay, so this is one sense in which proportional auction is robust. It is also robust in another sense. Okay, so if we keep binary value, but we relaxed common value assumption. Okay, so then suppose, right, bidder's expected value is known and are the same, but the seller can entertain any possibility for the correlation and for the information structure, right? It doesn't have to be common value at all. Still, proportional auction remains max to min optimal, right? And the common value information structure is in fact the min to max information structure. So that is the worst case in the min to max sense. Okay, so that's another sense in which it is a good idea to run a proportional auction. Okay, and finally, the final sense in which proportional auction is good is that, right, now going back to common value, in fact, the profit guarantee in the common value case given by the proportional auction will converge to the expected common value, which is the full surplus, as the market gets large, regardless of how information changes as we add more and more bidders. Okay, so in this sense, right, this is saying that even if we know exactly the information structure, we cannot improve the profit guarantee from the proportional auction by very much, because the profit guarantee is convergent to the full surplus at the rate of central limit theorem, which is 1 over square root of n. Okay, and we get 1 over square root of n because we are adding signals, we are adding independent signals. So very naturally, we will run into the central limit theorem in the worst case min to max information structure where all of the signals are independent. Okay, so I think I'm out of time. So let me just quickly wrap up. So first of all, so actually the very first max to min mechanism for the binary common value is constructed by Ben, Dirk, and Steven in 2017. And then these results that I have reported in these lectures really builds up on Bergerman, Brooks, and Morris 2017 in a sequence of paper that Ben and I are working on. Okay, and there are also a lot of aspects of robust auction that we have not discussed in these lectures. Here is a very incomplete citation of the literature. There are many other aspects of robustness, like robustness to strategic uncertainty, robustness to resale opportunities, that we do not have time to discuss in these lectures. Okay, so just to wrap up, so right, so first of all, we have given linear programs which can compute optimal profit guarantees over all information structures or equilibrium. Okay, and in many cases, the solution of these linear program, which are the max to min mechanism, is the proportional auction. This simple auction format which is exactly max true mean optimal in many cases. And in the case of common value, the optimal profit guarantee is unimprovable because it converges to the full surplus as the market gets large. Okay, so there's, of course, lots of open questions here, right? So for example, what if right here we have allowed every possible information structure? So what if there are some lower bound on the information structure? For example, we know for sure set bidders knows exactly their private value, right? That's one possibility for the lower bound. Then, right, it's interesting to also characterize the max to mean mechanism, for example, in the common prior setting. And then, right, of course, we can talk about simple mechanism which can guarantee a good approximation of the full surplus. The guarantee might not be exactly optimal, but they are still big enough. It's still a large fraction of the full surplus, for example, even uniformly across the size of the market, right? That's an interesting question to explore. And also other welfare criteria like minimax regret for social surplus. And we have assumed equilibrium for the bidding behavior for these, for our players. It's very natural to explore alternative, relax the strong equilibrium assumption, right? Something like rationalizability, or perhaps these agents which are adaptive. They are not, they play some heuristic learning rules. These are all interesting questions to explore for the robust auction design.